In this video, we'll look at a trick that we can use to solve ice chart problems that look at first glance like they need a quadratic equation, but can actually be avoided. So let's look at an equation. So A in equilibrium with 2B. And let's say we've got an equilibrium constant for this that is very small, 3.3 times 10 to the minus 5. In fact, when you've got these very small equilibrium constants, you should always start thinking about these tricks. So we're going to set up a situation here where we've got the initial concentration of A to be 1 mole per liter and the initial concentration of B to be 0 moles per liter. We can calculate the reaction quotient Q. So QC is the concentration of B at the instant in time over the concentration of A at that instant in time, and we can see that this is going to be 0 squared over 1, so that is 0. We know that Q is less than K. That means that the equilibrium will shift to the right-hand side, so we will take A and we will convert it into B. All right, so let's set up our ice chart. So underneath our equation, we can write I for initial, C for change, and E for equilibrium. And our initial concentration is 1 mole per liter and 0. From looking at the fact that Q is smaller than K, we know it shifts from left to right, so we will use up A and we will create B, and we got to remember the coefficients are 1 to 2, so we use up in a 1 to 2 ratio. At equilibrium, we just add those two lines together, and if we're sloppy with sig figs, we have 1 minus x, and we have 2x at the bottom of our ice chart. Then we go ahead and we set up the equilibrium expression, so Kc is the concentration of B squared over A at equilibrium. We are told in the problem, and this is the key factor, that this is small, 3.3 times 10 to the minus 5, and it's going to be equal to the concentration of B all squared over the concentration of A. All right, so at this point here, technically we have a quadratic equation, so we can just expand out and rearrange and use the quadratic formula and throw away one root and we're done. But the key thing to remember here is that if the equilibrium constant is small, that means that the value of x will be small because we're not going to make a terrible large amount of B. Why is that? Well, the equilibrium constant is the concentration of products over reactants. If the equilibrium constant is small, that means the concentration of products is small, and so the x itself is going to be small. So we can make this approximation here. If x is small, then we can say that instead of writing it like this, we can say it's equal to 2x squared over 1. So we are subtracting away a small number from a large number, so we can say that essentially we're just left with the large number. Now you can't throw away the x on the top, otherwise it wouldn't make sense. Why is this much easier? Well, if you're solving for x, this is going to be a piece of cake because all we got to do is divide both sides by 4 and square root. So x is equal to 3.3 times 10 to the minus 5 divided by 4 square rooted. And that gives us 2.87 or 2.9 times 10 to the minus 3. And if we look at that, we can say that actually that passes our original assumption, right? It's because we assumed that this was a small value, right? We were essentially assuming that 1 minus x is pretty much the same thing as 1. So, of course, if x is 2.9 times 10 to the minus 3, 1 minus 0.0029 is essentially just 1. So that is actually okay. We have a rule called the 5% rule that is a way that we sometimes use to see if this check is allowable. And let me call up another slide and let me explain how we use this 5% rule. So the 5% rule basically says as long as less than 5% has broken apart, we are okay. So we can calculate the percent dissociation. So the percent of the breakdown, and that is essentially the value of x that we got divided by the original concentration of reactants times by 100. And so in our problem here, our value of x was 0.00287. And our original concentration of reactants was 1, so we can see that's a very small percentage. We multiply by 100 to get a percent. That is 0.287%. And so since that is less than 5, we consider this to be a valid approximation.